Hi, I'm Bob Hanlon. I recently gave a talk to a group of professional engineers and asked who here took a course at the university level in thermodynamics, and everybody raised their hands. And then I asked who here truly understood the concept of entropy, and no one raised their hands. And oh, by the way, I didn't raise my hand either. There's clearly something wrong here, right? I believe that most of the students at the university level are capable of understanding thermodynamics. So that must mean that we as educators need to do a better job of teaching thermodynamics. But before we can do that, I think we need to do a better job of understanding thermodynamics. So why is it that 170 years after the founding of thermodynamics, we don't fully understand it? Well, I believe that a relevant quote here will start us down the path of understanding the situation and the problem. The quote is from Albert Einstein, and it goes like this: "If you can't explain it simply, you don't understand it well enough." Well, it seems clear that we don't understand thermodynamics simply. So what's the problem? Why aren't we there yet with this understanding? What's stopping us? Well, I believe that the root cause here is that there's a disconnect between the world of moving and colliding atoms and the world of classical thermodynamics. And that if we understand those connections better and close that gap better, we'd have a better understanding of thermodynamics and so be able to teach it better. Let me explain this more. Thermodynamics is a beautifully structured creation that's comprised of the first and second laws of thermodynamics, energy and entropy, work and heat, and such macroscopic properties of matter as temperature, pressure, volume, and mass, all perfectly tied together with calculus. Well, the reason thermodynamics has withstood the test of time is that it doesn't depend on any assumptions regarding the physics behind the equations. It was intentionally created this way since the early founders of thermodynamics in the mid-1800s didn't want to speculate about the atomic theory of matter, since atoms hadn't yet been discovered and wouldn't be until decades later. So while this design helped early on and helped solidify the strength of thermodynamics, it's clearly not helping today. In fact, it's the problem. It left us with a large gap between the equations we learn on the left side of this slide and the underlying physics of moving atoms on the right side. Because of this gap, we don't fully understand the physical world well enough to explain thermodynamics to our students. This then leaves the students looking at thermodynamics as an indecipherable black box that intimidates them from using thermodynamics to solve problems. So what's to be done here? Well, clearly we need to close the gap, and the path forward and the guiding light here is a quote that I loved from Richard Feynman that goes like this: "All things are made of atoms, little particles that move around in perpetual motion, attracting each other when they are a little distant apart, but repelling upon being squeezed into one another." In that one sentence, you will see there is an enormous amount of information about the world if just a little imagination and thinking are applied. The bottom line is that we know much more about the atomic world today than the founders did in the mid-1800s. And it's now time to use this knowledge to make thermodynamics more understandable. So what does a better approach look like? Well, let's look at the big picture here. What I'm suggesting is that we build the syllabus of thermodynamics on top of the foundation of an atomic theory of matter. Let me go into a little bit more detail on that here. First, I believe that we need to establish as a first tier of the syllabus the atomic theory of matter and explain the world of atoms and how they behave around each other. And then we can build on top of this foundation the second tier by teaching how the atomic world gives rise to energy and entropy, heat and work, and the laws of thermodynamics. In my first book, Block by Block, The Historical and Theoretical Foundations of Thermodynamics, I worked to create this connection between the atomic world and these concepts, the tier 2 concepts of thermodynamics. So then we move on to tier 3. And in tier 3, we look at the applications which can be deduced from the contents of tiers 1 and 2 involving the atomic theory of matter and the laws of thermodynamics. This is the job that has not yet completely been done, by anybody that I can see at least. I've read much and have yet to see somebody pull all of this together. And what are some of the applications I'm talking about here that we need to tie to the atomic theory of matter? Well, these are such things as phase change, the existence of critical points, the Joule-Thomson effect, the Clausius-Clapeyron equation, equilibria, Gibbs energy, maximum work, power cycles, and so on. I believe if students understood the connection between these applications here and the atomic theory of matter and the tier 2 concepts of thermodynamics, they would understand thermodynamics better. As you can see, some of the applications listed here you have already contributed to me in previous communications I've had with you all, in which you shared with me your pain points or stumbling blocks that you've experienced with trying to learn and teach the topics here in tier 3. My belief is that the direction of this education should be from the bottom up. It must start with atoms and molecules that move and interact with each other. In other words, we shouldn't be teaching the concept of entropy in tier 2 by using the Carnot heat engine from tier 3. This heat engine is difficult enough to understand as it is, and attempting to use it as a way to introduce students to entropy is simply not effective and in fact can be quite confusing. So why do all of this? Why seek to improve thermodynamics by basing it on the atomic theory of matter? Well, simply put, it's there to be done. It hasn't been done yet. It can be done. We can explain it this way. Let's figure it out. And there's another reason why I think we should do this. The better one understands how to use a tool, the more likely they will be to use it, and the better the solution to the problem will be. I believe that the atoms first approach to teaching thermodynamics will help the students to better understand thermodynamics and also enable them to more confidently, proactively, creatively use thermodynamics to solve the problems that they'll face as professionals. And I believe that the solutions they arrive at will be much better than they are today. So this is my hypothesis, that if we start with the atomic theory of matter, we can improve and better teach thermodynamics to the students. Do you agree with me? Let me know. And to those of you who have begun to use my book to enhance the education of your own classes in thermodynamics, please let me know how that's working out for you. That's it for now. Until my next video, goodbye.